This is a question from data structures. If G be an undirect connected graph with distinct edge weight, the important point here is distinct edge weight such that maximum weight and minimum weight of the edge is given by emax and emin respectively. Then which of the following statements are true? And we are given four statements. So first of all, let's try to understand each options. The first one is every minimum spanning tree of G must contain emin and emax. So first of all, what is minimum spanning tree? That is MST. It is a minimum weight spanning tree which consists of subsets of the edges which are connected, an edge weighted undirected graph that connects all vertices together without any cycle and with the minimum possible total edge weight. So we can say that it is a tree whose edge cost is minimum such that the edges that are added do not form a cycle and it includes all the vertices of the graph. This is a minimum spanning tree. Now let's see each options. Every minimum spanning tree of G must contain emin and emax. So let's try to see if this is true or not. To construct a minimum spanning tree, let's consider the usage of a Kruskal's algorithm. In Kruskal's algorithm, what happens is we sort all edge weights in increasing order. Then we take each edge and add it to the minimum spanning tree, provided it do not form a cycle. If it forms a cycle, then that particular edge which caused the cycle will be usually the one which is having the most weight in the current minimum spanning tree that will be removed. So this is the basic concept. Now let's draw a simple graph. This is a simple graph and the basic concept here told is that all the edges are having distinct weights. Assume 1, 2, 3, 4. All the edge weights are distinct. Now based on the Kruskal's algorithm, the minimum spanning tree can be constructed by adding the edges whose weights are in increasing order only. So we will add first AD whose weight is 1, then we will add AB whose weight is 2, then we will add BC whose weight is 3. If we add DC, then it forms a cycle. So this is the minimum spanning tree for this corresponding graph. So from this we can say that Emin, the minimum weight is 1 and that is included in the graph, but Emax is not included in the graph, not graph tree. So from this we can say that every minimum spanning tree of G must contain emin and emax. This is false. It is not at all necessary that it should contain both emin and emax. Now let's see option B. If emax is in minimum spanning tree, then its removal must disconnect G. Yes, this option is true because from the basics of Kruskal's algorithm, we see that if the graph is forming a cycle, then we will remove it. So from this concept, we'll try to understand how can Emax be present in a minimum spanning tree. Suppose let's consider this graph. The weights are 1, 2, 3. Sorry, the edges are A, B, C, D, E, F, G, H. And the weights are 1, 2, 3, 4, 10, 5, 6, 7, 8. This is the graph. So if based on this, if you're based on Kruskal's algorithm, if we draw the minimum spanning tree, we'll add 1, then the edge 2, then the edge 3. This is having weight 1, 2, and 3. If we add 4, it will form a cycle. Then without adding this particular edge that is having weight 10, even though it is having the maximum weight, we cannot construct the minimum spanning tree because removing it will disconnect the tree. So then we'll add this uh, edge which is having most weight, then we'll add edge which is having weight 5, then 6, then 7. I'm just noting down the weights only. It is corresponding to the vertices also. So this is the minimum spanning tree for the given graph. So removal of this vertex, which is emax, will disconnect the graph G. So if emax is in minimum spanning tree, then its removal will disconnect the graph G. This option is true and this option is false. Then no minimum spanning tree contain emax. This is also false because this diagram proved that this statement is false. Then G has a multiple minimum spanning trees. This is also false because we are having distinct edge weight. So since we are having distinct edge weight, we will be adding only distinct values. So multiple minimum spanning trees will not be possible. So based on the options, only option B is the correct answer here.